let's talk about Green's theorem. Green's theorem. All right, so do you guys remember like how in Calculus 1 we had the fundamental theorem of calculus part 2? And here's a couple of different forms of it. Well, the form that I learned, so we're looking at this here, but the form that I learned for this actually looks a little bit different. If we have the definite integral from a to b of some function f of x, integration with respect to x, that equals the same thing as the function evaluated at the upper bound of integration minus the function evaluated at the lower bound of integration. That's the fundamental theorem of calculus part 2. Well, in calculus 3, we have something a little bit different shown here. Now, that's it. So we'll look at this to preface our exploration of Green's theorem. Now, here's a textbook definition of Green's theorem, circulation form, as Green's theorem comes in two different flavors, that is, circulation form and flux form. Now, if we let C be a simple closed piecewise smooth curve oriented counterclockwise that encloses a connected and simply connected region R, if vector f equals f for the x-coordinate and g for the y-coordinate, and f and g have continuous first derivatives on R, then the following is true. We have our circulation integral, which in this circle here just means that this is an enclosed circle, right? We have the circulation integral, and let's just try to like unpack what's going on here, right? We're moving from left to right, so let's look at this. Okay, we have vector f times um, a vector, the derivative of vector r, right? These are the steps that we're taking along path C, and then vector f is like the wind, how much it opposes and or goes against it, the wind, the force, right? Outlying factors, right? And we're dotting it with dr, our velocity vector. And then as we move to the right, we can see that this changes. Oh, okay, so then this vector f is now we're now looking at just the coordinates, and it's in these square brackets here to show that it's a vector, right? Dotting it with dr, our velocity vector, and this is just dx dy with the same square brackets, and then we move to the right more, and it changes orientation. We have still, it's an enclosed integral, but it's f dx plus g dy, okay, and then it changes, and this is the Green's theorem equivalent. That is the double integral for region R equals the partial derivative of g with respect to x minus the partial derivative of f with respect to y. And the note here is that if vector f is conservative, then um, then f sub y, which is really this is a different notation for the partial derivative of f with respect to y, equals the partial derivative of g with respect to x. And then I put it in Leibniz notation, and I did steal this chemistry notation to show that this is the same exact thing. So take that, chemistry, because, well, I'm just going to borrow that. So rather, give me that, chemistry. Anyway, I used it for the sake of mathematics here, but this is it in Leibniz notation. But if vector f is continuous, then the partial derivative of f with respect to y equals the partial derivative of g with respect to y. Hence, by Green's theorem, if vector f is a conservative vector field, then such is true, and this is just showing that that um, that it's going to equal 0. So if vector f is conservative, then our result will be 0. When we investigate the Green's theorem equivalent. So I think now is a good time for a mathematical meme that I stole from Google. Um, it shows, this is a meme. It's a mathematician, and he shows the expression, and he goes, so Green's theorem relates a line integral on a simple and closed curve to a double integral of the difference of the partial derivatives of the components of a vector valued function. And that drag to move is not supposed to be there, but whatever, it's a screenshot. And then the engineer says, well, Green's theorem says that all of the little inside swirls combine into one big outside swirl. And that's basically what he's saying is that if you have like some sort of pinwheel inside of like a vortex, right? Like that if you put a bunch of microscopic pinwheels inside and you calculated the forces of all of the little pinwheels, the swirls, the vortexes inside of the big vortex, all of it would be the same amount of force combined of all these little tiny pinwheels, the tiny vortexes, as it would be the same exact force as the force on the outside of the vortex. So the joke here is you have a mathematician that gives us a well put together mathematical definition that is very sound mathematically, and it's very finite, and it's definitive, and it's a little bit more complex and intricate, but it's absolute in its definition. And then you have an engineer who is just this it's it sounds like he's a madman. So very funny joke. Ha ha he he ha ha ho ho ah ha ha ha. And yeah. So let's keep the ball rolling here. So um we look at the expression, the partial derivative of g with respect to x minus the partial derivative of f with respect to y. Well, that's called the two-dimensional curl of vector f. Well, a curl is a measure of how much a vector field is trying to spin or rotate around a specific point. Curl itself is measured as a specific point, but when you integrate a curl over an entire region, it tells you the total net rotation around that region. Um, Circulation has to do with moving you along a curve, and flux has to do with moving perpendicular to a curve at a 90-degree angle. Um, if we have curl f, um, well, we could say that, well, that equals the partial derivative of g with respect to x minus the partial derivative of f with respect to y. And if the curl of vector f equals 0 on a region R, then vector f is irrational on R. And so that leads us into the second form of Green's theorem, the different flavor, and that is flux form. If we let C be a simple closed piecewise smooth curve oriented counterclockwise that encloses a connected and simply connected region R in the plane, we can assume that vector F uh, equals F and G, where F and G have continuous first derivatives on R. Then, this is supposed to have an N. Can I put that there? There we are. Then this equation is true, and we have the flux integral, and we have Green's theorem's equivalent. So if we look at this and we can move from left to right again, we have well, our circulation integral here, and we have we have vector f, and we have um, our normal vector. And we can see how these things change. We're dotting them together, and we can see how these things change. This is the arc length. And we can see how these things change um, as we move to the right. The vector f turns into this, and then the normal vector turns into, well, normal vector and ds, it turns into this. And this is subtraction, so it turns into that. And then this is the Green's theorem, the Green theorem's equivalent, which is supposed to have an r right here. And just write that in there. And that is the double integral. And within inside of the double integral of region R, and then within the integrand, we have the partial derivative of f with respect to x plus the partial derivative of g with respect to y. And the expression, the expression in the integrand, the partial derivative of f with respect to y plus the partial derivative of g with respect to y, is called the two-dimensional divergence of vector f. Divergence of vector f equals the partial derivative of f with respect to x plus the partial derivative of g with respect to y. And if the divergence of vector f is 0 on a region R, then R is source free. All right, so a couple things to unpack there. The first thing that I want to say is that in vector calculus, divergence is not the same thing as, well, like I remember when we were doing like calculus 2, we had, when we were doing calculus 2, we had divergence and convergence when we came to summations. So like, if a value converged or added up to a finite sum, then it was convergent. If it exploded off into 0, or it was, erratic, oscillating erratically, and it was not definitive, it was not finite, then we would say that it diverges. This is not that. This is totally different. In vector calculus, divergence means that it spreads out from a point, okay? But the source, like the source of something, um, well, source free means nothing is being created nor destroyed inside of an area. So when we think of like a source, right? I'm gonna draw, let's see here. I'm gonna draw, this is an R2. So we have our X and Y. If we have like the source of something, right? Like a source in a vector field might look like this, right? We have arrows coming out and the arrows are coming from a source. In this case, they're coming from the origin. But source free means that nothing is being created nor destroyed inside of that area. So whatever flows in must flow back out. Mathematically speaking, in this context, source free means that a region R has a divergence of 0 everywhere within it, indicating that the total net flux flowing out of any closed curve or surface in the region is going to be 0. Let's talk about steam functions. And of course, in here, in vector calculus, divergence means spreading out from a point. Um, so it's different in this context. But if we're let's talk about building a stream function. A stream function of a vector field f, if it exists. I'm pretty sure there's supposed to be a little arrow up there. If it exists, is called psi, and it has the following properties. The partial derivative of psi with respect to y equals f, and the partial derivative of psi with respect to x equals negative g. Note that the divergence of psi can be written as follows. And well, if you want to take a look at this here, we have the divergence of psi equals the partial derivative of f with respect to y plus the partial derivative of g with respect to y equals the partial derivative of f with respect to x and the plus the partial derivative of g with respect to y, and it's just sort of changing orientations here. But then watch how it changes. It turns into the partial derivative with respect to x times the partial derivative of psi with respect to y plus the partial derivative of plus the partial derivative with respect to y times the negative partial derivative of psi with respect to x, and the partial derivative of psi equals the partial derivative with respect to x times the partial derivative of psi with respect to y minus the partial derivative with respect to y times the partial derivative of psi with respect to x equaling 0, since the partial derivative of psi with respect to x and y equals the partial derivative of psi with respect to y and x. So the existence of a stream function psi guarantees that the vector field has 0 divergence and is source free. Now this is where we get to have some fun. So here's an example. It says to evaluate both integrals in Green's theorem, circulation form, for vector f with our x coordinate being -2 times x times y and our y coordinate being x squared. Now our region is bounded by y equaling x times 2 minus x quantity and y equaling 0. I have written out Green's theorem in circulation form right here, and here at the end in green is Green's theorem. Um, so let us take a look at what's happening here. The first thing that I'm going to do is I'm going to draw this out graphically speaking. We're going to draw out our curve y equals x times 2 minus x. Okay? Um, and that's going to be a parabola. That's going to be a parabola. So it's going to come up and then it's going to go down. So this is our parabola, but this is the region that we're looking at because it's bounded by this curve right here and y equals 0. And when y equals 0, that's just our x-axis. We're looking at this region, but this y equals x times 2 minus x crosses over the x-axis. Here at the origin, one point here, and Well, it has its vertex and it peaks right about here, and it crosses back down into quadrant 4 at this point here. And it crosses back, it crosses, and the parabola falls back down and goes into quadrant 4 right here at this point. And it turns out that this point right here is actually 2. So we can parameterize this curve in such a way where we can say along y equals x times 2 minus x from 0, 0 to 2, 0. So we're moving along the path from 0, 0 to 2, 0 because that's where it crosses over. So we're moving along the path like this. We are going in we're going in a clockwise direction. Then um, then we have to look at the boundaries when we move across the x-axis back towards the origin. So that would be this way. So we move along this way, but then so we move along the curve from 0, 0 to 2, 0, but then we move along y equals 0. We move along the x-axis from x equaling 2, y 0 to 0, 0, the origin. So we're moving across two curves here. So at this point, we're going to stop and we're going to ask ourselves, we want to analyze this. What does my decision to orient C in this way mean to my answer? Well, um, it's oriented clockwise. The red arrows are oriented clockwise. I've induced a clockwise rotation, so my answer is going to be negative of what it should be, because as we remember here, just kidding here, um we're talking about something that's being oriented counterclockwise. Well, here we're orienting it clockwise. So what that means is that that my answer is going to be negative of what it should be. It's going to be negative of what it should be. So let's investigate the first path, that is path 1. And we can call it C sub 1. C sub 1 is going to be vector r sub 1 of t. And in this case, my x component, it's just going to be t, right? And then my y component, it's going to be, well, I'm going to change all of my x's to t's because I set my x equal to t. So here, it's going to be, well, y equals x times 2 minus x, and I'm going to switch out all those x's for t's, so I'm going to have t times 2 minus t. Okay, and we're looking at this in a situation where this is 1 and this is 2 here. So we know that t has to be in between 0 and 2. That is, 0 is less than or equal to t, and t is less than or equal to 2. So for c sub 1, vector r sub 1 of t equals xt, and then I'm going to distribute that t amongst the parenthetical statement, so it's going to become 2t minus t squared. It's still going to be, the t is still going to be between 0 and 2, of course, but we are going to need to take the derivative of this. So we want the derivative of vector r of t, and if r of t, vector r of t equals, um, well, we need the derivative of the statement. So what's the derivative of t? That is going to be 1. And what's the derivative of 2t minus t squared? Well, the derivative of 2t is going to be 2. And the derivative of negative t squared is going to be negative 2t. So in full, the derivative of that vector, is going to be x1 and y2 minus 2t. Now, um, that's our path 1, but we're not off the hook because we need path 2, right? Now we're going back this way. Um, so this is path 2, and we'll call it c sub 2. That is vector r sub 2 of t. Um, well, this is linear. Um, x is 2 and y is 0. We're looking at our start point. We're starting right here at x2, y0. So we start at 2, 0. Okay. And then we're going to add t times how far I move. So t times the vector, but it's going to be how far I move. So um, let's see. We are going to, for the x coordinate, the final placement is 0, 0. So x 0, y 0 is the final placement. That's where we end up, but we have to subtract the initial point of where we started. So that's so it's final minus initial in the x coordinate. The final point in the x coordinate is 0 minus the initial point, which was 2. And then for our y, we started, well, y was initially 0 and it ended as 0, so it's going to be 0 minus 0. This is going to equal, so again, it's t times, so we have, let's do this. Starting point, this is our starting point, and then this is t times how far I move. So all we need to do is just distribute that t, and then add them together. So as it turns out, this is going to turn into x being 2 minus 2t and y being 0. And well, t gets replaced with x, and then well, here t will be between 0 and 1. Right. And then now I need the derivative of vector r sub 2 of t. So let's take the derivative here. What's that going to be? Derivative of, oh, that's going to be negative. So this is going to be negative 2 and 0 is just going to be 0. All right, so that's our derivative. So now let's get this thing set up. It's a circulation integral here. Curve C, vector F dot velocity vector equals what? So the first integral is going to be between 0 and 2. And one thing to note, this here, this point right here, that's 1. So this is between, this is going, this right here, 1, this is here, it's 2. So so the first integral, look at the first integral is between 0 and 2. And the first thing that we need to do is we need to account for that negative 2. Um, and you might be like, where is that negative 2 coming from? The -2 is coming from right here. So that is going into the equation. Then we're grabbing this, we're going to multiply it by this here. So we're going to multiply it t times 2t minus t squared. And then for y, it's going to be t squared. And let's use some colors to show what's what, where, and why. 2x, right? So t is turned into x, so that's why these t's are the same, right? Where did we get the 2t minus t squared? That's, well, from right here. Oh yeah, same replacement for x. Y is here, and why is it squared? Well, the squaring is from the square. Why is the y component of t squared? The squaring is from here. Now we're going to dot this with the derivative of what we found for r right here. dt on the end of that there. And, well, this is going to be path 1 with vector r sub 1 of t. Now to this, we add our other integral. We add our other integral going from 0 to 1. Same thing, we have to account for this -2 right here. But in this case, x is 2 minus 2t. Where is it? Right here. And y is 0 right here. And that's our that whole thing is our x component. And for our y component, we're going to grab our y. And well, y is x. And here we've established that x is 2 minus 2t. Okay, but we have to square it because that's the rule in the original vector. So we square it, and then we dot it with the derivative. So I will dot this with -2, 0, dt on the end of that. And what this is here is this is path 2 with vector r sub 2 of t. So this 2 is the same as this 2, and I feel like everything else is fairly clear. Maybe this, oops, this power of 2 can match. Now we can write this out in full. So what does this equal? Well, let's start working through the first integral from 0 to 2. We need to multiply everything in the x component. So this is going to become, this 2 is going to go, this is going to become 2t squared. This is going to become, well, this 2t squared minus t cubed. Then multiply this -2 to both, which is going to be -4 t squared minus, or rather plus t cubed. right? So it's going to become, wait, no, wait. It's going to become negative, this is going to become, this negative 2 is going to get, no, well, first we'll do t. T is going to get applied to 2t. This is going to become 2t squared minus t cubed. Then we'll apply this. Negative 2 is going to get multiplied. Negative 2 is going to get multiplied. Okay. This is, so we're going to have to multiply everything in the x component here. This is going to become negative 4 t squared plus 2 times t cubed. And then for the y component, this is just going to be t squared. And we're going to dot it with the same thing. To this, we shall add our second integral from 0 to 1. But we're going to have to work out what's going on in here, which this is just going to all go to 0. Now that's easy enough. And what else? We're going to have to square this. And this is going to stay the same. So 0, this is minus squared. So what is this? How does this go again? A squared. I'm pretty sure, wait, oops. I'm pretty sure it's going to be what? A squared minus b squared. Or a minus b squared. A minus b quantity squared. So what's going on? 4 minus 2 times 2 is 4. Times 2 is 8. But there's a b, so it's t. So 4 minus 8t plus b squared, which is 4t squared. And dot it with this stays the same. Okay. So this is what we're left with. So this is the setup that we have now. That whole thing. Let's grab that. Let's just grab that. And I'm moving it over here. Because I just am. We need room to solve for it. Oh, what will happen? Well, we're dotting this, so let's see. 0 and 2. What's going on with the x components here? That's going to stay. So it's going to be this times this times this, and then add them together, I think. Plus this times this. 2t squared minus 2t cubed dt. What is this? 4 minus t squared plus 2t cubed plus 2t squared minus 2t cubed. Integration with respect to t. And then 0 times, well, this is going to be, hold on, wait. Integral from 0 to 1, 0 times negative 2 is 0 plus 0, guys, because this times 0 is 0. So it's the integral of 0. Wow, this whole thing's gonna go to 0. But let's turn our attention to this here. This first one. This first one, let's combine like terms. Positive 2t cubed, negative 2t cubed. What are we gonna have? What's in store for us? The definite integral from 0 to 2 of negative 4 times t squared plus 2t squared. Integration with respect to t equals definite integral from 0 to 2 of negative 2t squared, I think, integration with respect to t. Oh yes, negative 2 can get factored out times the definite integral from 0 to 2 of t squared. Integration with respect to t equals negative 2 times t squared, just kidding, times t cubed over 3, evaluated from 0 to 2, I think. What is this going to be? 2 times this whole thing. That is 2 raised to the power of 3 over 3 minus 0 raised to the power of 3 over 3. Hey, look, this gets zeroed out. So it's going to be 2 times 8 over 3. No. What is it? 2 times 2 times 2 times 2 is 4, times 2 is 8, times 2 again. So, well, I've already started this, so let's do this. 3 equals, oh, this is a negative 2. What am I doing? I forgot the negative sign. Negative 2. Ah, there we go. Negative 2. This is going to be negative 16 over 3. So, this is our answer, kind of. So the path is oriented. Remember how the path was oriented clockwise? The path was oriented clockwise, but it should be, according to our theorem, it should be oriented counterclockwise. So, since I oriented the path backwards, the correct answer is actually going to be positive 16 over 3. And that's our answer. But, okay, so that's how I would find this, right? That's how I would find this. But let's do this. Let's try this. Let's try this. This is our answer. Let's try this with Green's theorem directly. So here's Green's theorem directly. And let's apply this to that same exact problem, right? We're going to do the same exact problem, but we're going to do it with Green's theorem's equivalent. So, let's run it. We're going to apply it to the same exact problem. So here, f of x and y equals negative 2xy. We just want to see how much easier this is with Green's theorem. And so we have f of x and y is negative 2 times x times y. And then g of x and y equals x squared. And that means that the partial derivative of f with respect to y equals, oops, there we go, equals what? Partial derivative of f with respect to y, negative 2x, and then the partial derivative of g with respect to x equals 2x. And then we're going to draw the same region here. Okay, what's up? We're going to apply Green's theorem's equivalent. So we're gonna apply this. Oops, we're gonna apply this thing here. First integral is going from 0 to 2, right? That's our x-axis. Second integral is our y-axis. So it's going from 0, because we start at the origin, but it's going to up to this curve. And this curve, it changes, so it's x times 2 minus x. X minus, no, wait, what am I doing? X times 2 minus x. X times 2 minus x. Hey, look, it's letting me draw with my cursor. I wonder why that is. Anyway, now we're trying to set this thing up, and we're going to follow Green's theorem. Well, let's do that, but let's do that in blue. You know why? Because blue is a great color. In my opinion, blue is the best color. Um, so let's see. Okay, so we're gonna look at this. Partial derivative of g with respect to x, partial derivative of g with respect to x. We found that to be 2x. So we're gonna have 2x, right? And then we're supposed to subtract there. Let's see. And then we need to subtract the partial derivative of f with respect to y, which we found to be negative 2. So I'm just gonna put a negative 2 in there. And well, this here is the y-axis, so this is going to be dy, and then this here is the x-axis, so this is going to be dx. Okay, we could do some simplification then. This is going to become a big plus sign, so this is going to be 4x. And honestly, I'm not going to put that there. I want y'all to be able to see the work. So, simplify this 4x dy dx. Let's make it parenthetical. Oh, let's work this thing out. First integral. This is going to become, upon integration, 4xy evaluated at its bounds. This is integration with respect to y. So y equals 0 in the evaluation bar, and that's the lower bound of integration. The upper bound integration is going to be, well, let's distribute that. What is this? 2x, y equals 2x minus x squared. Yes, let's do that. Integration with respect to x. And, well, we plug this thing in. Evaluate it via the fundamental theorem of calculus. What is this going to turn into? I don't know. Let's find out. that. It'll turn into that. This is going to turn into 0. See, 0 to 2. What is this? 8x squared minus 4x cubed. 4x cubed, I think. Okay. Let's simplify this. Linearity rule. Constant multiple rule. Constant multiple rule. 8 times x cubed over 3 evaluated from 0. Well, I should say x equals 0 at the lower limit, x equals 2 at the upper limit, minus 4 times x raised to the 4th over 4 evaluated from x equals 0 at the lower limit, x equals 2 at the upper limit, I think. And I'm not even going to bother to apply the lower limit of integration for either of these. So this is going to be 8. Well, I am, but I'm not. It's 0. That's actually a philosophical mathematical question. Actually, you know what? I'm not just going to shut up and do the math. See, 8 times 2 times 2 times 2, 8 over 3 minus 2 times 2 is going to be 16 over 4 minus 4 times 16 over 4, which can be simplified to another 8 equals 8 times 8 is 64, right? 64 over 3 minus 4 times 4 equals 64 over 3 minus 16. Well, the 16 needs to be multiplied by 3. What is 64 multiplied by 3? 32 plus 16. 32 plus 6 is 48, I think. 48 over 3. Oh gosh. Do that in my head, can I? Do I have the brain power? 64 minus 48. Oh, I was gonna have a 6. Is it 16 over 3? 16 over 3, positive 16 over 3. Hey, isn't that the same thing as this? Yes, it is. So that's how you do that with Green's theorem's equivalent. That is how you do it with Green's theorem. And that was a lot easier. You didn't have to do this path and that path. You just had to look at it and say, hey, this meets the constraints for the application of Green's theorem. And so we're going to use Green's theorem. It's a closed curve, and we will. So can do a quick side by side. One of them was significantly less work. This one says calculate both integrals in Green's theorem flux form for vector f equaling x and y, where the region is x and y, x squared plus y squared is less than or equal to 4. That's a circle. So that's a circle with radius 2. Because we know from the Pythagorean theorem that a squared plus b squared equals c squared. And here is x squared plus y squared equals, well, I guess is less than or equal to 2 squared. So let's draw it out. Let's draw out that region. And let's just try to see what's going on. So this is radius of 2 though. So let me put 1, 2, 1, 2, 1, 2. Wait, that looks, that's fine. It's actually -2. -1, -2. All right. And this is the region within, guys. The region within. It's supposed to be shaded. Yeah, so this is radius 2. And then this is going to be curve C. Okay, that's the curve. So let's just take a look at this, right? We're doing this in flux form. So this is Green's theorem. Okay. All right. Okay. Line integral. Let's talk about the line integral. Let's talk about the line integral formula. So this is going to go from, well, this is the closed curve C, and okay, so we're going to look at this and we're going to look at this. I'm putting it in two ways. That is, let's see, vector F times the normal vector, and this is going to equal F dy minus g dx. All right, and let's see, this is a circle. So x is going to be cosine and y is going to be sine. But this is a situation of radius 2. So let's parameterize. I think that's the correct mathematical terminology. What I'm doing is I'm going to try to find our coordinates for vector r of t. And well, this is a vector here, and we're going to deal with cosine of t and sine of t. And well, remember that we have a radius 2. So there's going to go a 2 in front of each of these. All right, to scale it up larger. And because a full revolution around this circle is 2 pi, 2 pi is a full revolution, no Bolshevik. And that means that 0 is going to be in between, excuse me, that means that t is going to be in between 0 and 2 pi. Um, this is our x, and this is our y. And we need the derivative. We need the derivative vector of vector r of t. That is vector r prime of t. what's the derivative of cosine of t? It's going to be negative sine of t. So I do believe that this is going to be negative 2 sine of t. And what's the derivative of sine? That's going to be cosine. So this is going to be 2 cosine of t. And well, this here is our dx. Negative 2 sine of t is dx. 2 cosine of t is dy. And well, this is equal to our velocity vector, dr. So now we need to use this formula. We need to use this formula. We're setting up the integral, right? And we know that t is between 0 and 2 pi. So that's the integral from 0 to 2 pi for f, f, and f dy minus g dx. Okay, f is the same thing as x, so I'll say x dy and minus g is the same thing as y, so y dx. And this is true since um, since f equals x and g equals y. So here there's x, and there's y. X, x, y, y. But what about dx and dy? You know, like what about them? How do I do this? Wait a second. How do I take this color? Hello? I want this one. And well, here's dx, and here's dx, and here's dy, and here's dy. So we can set this up with more detail. That is, the integral from 0 to 2 pi equals x, which is set to 2 cosine of t, times dy, and dy is 2 cosine of t, minus y, which is 2 sine of t, times dx, which is negative 2 sine of t. And then what? Something goes on the end of that. Integration with respect to t. And then this can be simplified to become the integral from 2 to 0, from 0 to 2 pi. 2 times 2 is 4. Cosine times cosine is cosine squared of t, minus 2 times negative 2, which is negative 4. So it's going to be plus 4. Sine times sine is sine squared of t. Integration with respect to t. So I can factor out a 4 from both of these. So this is going to be the definite integral from 0 to 2 pi of 4 times cosine squared of t plus sine squared of t and what's this? A Pythagorean identity has revealed itself to us. Cosine squared of t plus sine squared of t equals 1. So, having identified that, we're going to have the definite integral from 0 to 2 pi of, well, 4 times 1, which is 4, dt equals 4t evaluated from 0 to 2 pi. Well, we're going to have 4 times 2 pi minus 4 times 0 equals 8 pi. And this is our answer. It's 8 pi worth of flux. And the flux is outward because it's positive. We're going to look at Green's theorem's equivalent. Now, we just did the flux integral. This and this. This is the same thing by definition as the flux integral, but we looked at these two. And now we're going to look at the Green's theorem equivalent because we found it like this and that was fun, but there's an easier way to do it. Because if we have the double integral for region R, the integrand we're going to have the partial derivative of f with respect to x plus the partial derivative of g with respect to y. Okay? Now, the question, wrong question. The question, well, it says vector f equals x and y. All right, so, well, vector f is vector, oops, vector x, y. And we know x and y. Hey, x is another name for f and y is another name for g. Right? So, so if that's true, then we can find pretty easily the partial derivative of f with respect to x because that's going to be 1. And the partial derivative of g with respect to y, hey, that's also going to be 1. And then we can draw a visual here just to get eyes on this. This is a circle of radius 2. All right. It's the same thing. We're just going to use Green's theorem to solve it because it makes it a lot easier. All right. Um, so, so what have we here? We can do the double integral, find our region R of the partial derivative of f with respect to x, which, you know what? We know that's 1. I drew my ones differently here. And then the partial derivative of g with respect to y, hey, that's also 1. And so, well, what we're looking at is this a situation with the double integral of 2. And so we can take this, right? You could just factor out that 2. 2 times the double integral of r for 1dA. And the area of region R, well, the circle has a radius of 2. The circle has a radius of 2, and so let's just do this in a different color. We could just look at this here. So this is going to give us the area of region R. The area of region R, the circle, right, has, well, the radius, it equals 2. And so the area equals pi times the radius squared, pi times 2 squared, that equals 4 pi. And so And so what this actually is going to equal is it's going to be 2 times 4 pi. And we'll do that in purple. Here, actually, let's just do this. Oh, we love the mechanics of Sketch.io. So now we have 2 times 4 pi, and that equals 8 pi. So by using by using Green's theorem's equivalent, we calculated the same answer twice. Well, one of them was a lot easier and a lot simpler. So that's why Green's theorem is very useful. And again, this is 8 pi worth of flux, and it's outward flux since it's positive. Uh, you might ask yourself, like, what's the difference between outwards flux and inwards flux? Outward flux is the vector field crosses the boundary moving from the inside to the outside of the region, resulting in a positive net value. Inward flux is the vector field crosses the boundary moving from the outside to the inside of a region, and that results in a negative value. Um, Inward and outward flux, they describe the flow of the field, such as an electric or magnetic field, across a closed surface. So by convention, flux lines entering a surface represent an inward flux counted as negative, and flux lines exiting the surface represent an outward flux, which is counted as positive. And I know that we established that before, but you know what? We're establishing it again. So let's do another one. This one is in polar coordinates. This one says calculate the circulation around the outward flux through the boundary of the region. Vector F equals 2x plus y and x minus 4y. R is quarter annulus, and R is, well, instead of x and y, it's r theta, so it's polar, where R is between 1 and 4, and theta is between 0 and pi over 2. And something to note is that r r is the well, capital R is describing a region that's enclosed by these values, and and r theta, well, this is polar coordinates, so r is, when you think of polar coordinates, it's concentric circles. So r is the number of circles, and theta is the angle between. So let's do some work on this. This is um this is the polar coordinate plane. But we know that we're going to be doing this in quadrant 1. And we know that we're going to be doing this in quadrant 1 because it says that 0 is between it says that theta, because it says theta is between 0 and pi over 2. Well, when we deal with the unit circle, it goes it goes 0, pi over 2, pi, and 3 pi over 2 because we're dealing with radians. And since that's the case, if theta, the angle, is going between 0, and it's going to be in between 0 and pi over 2, that means it's going to be in quadrant 1. So um, polar coordinates is concentric circles. So we can imagine this instead of like tiles or instead of squares, now we have circles. So 1, 2, 3, 4. So like 1 circle, 2 circle, 3 circle, 4 circle. And r, little r, well, this is, let me be clear here. Capital R is the region described. Little r is the amount of concentric circles. So we know that little r is the region between, it's describing the region. And this is 1. So this is the first circle here. And we know that it's going to be in between pi over 2 and 0. So the first circle would be right here. And it's between 1 and 4. So the second circle would be here. Right? So this is the region. This here is then the region that's being described because it's the concentric circle. Because it's the circle. Because the first circle and the fourth circle. Because polar coordinates, and it's between the angle 0 and pi over 2 radians. And this is our region. It's a closed region. It's closed by 0 and pi over 2. So we can see that the region that's described, and we need to find well, what's the circulation? What's the circulation? What is the circulation? Green's theorem in circulation form. Here's Green's theorem in circulation form, so we are going to grab that. That is the partial derivative of g with respect to x minus the partial derivative of f with respect to y. What does this theorem mean to us? Well, it's Green's theorem in circulation form, but we need to know the partial derivative of g with respect to x and the partial derivative of f with respect to y. Well, this is f and this is g. And we want the partial derivative of g with respect to x. Partial derivative of g with respect to x. Well, the partial derivative of g with respect to x is 1 minus 4 times. Wait a second. Yeah, x is 1 minus 4 times 0. So it's going to be just 1. Okay? Then we need the partial derivative of f with respect to y. Partial derivative of f with respect to y. 2x gets treated as a constant. Well, x gets treated as a constant. 2 is a constant. Constant multiple. 0. 2 times 0 is 0. Plus 1. Y is 1. The partial derivative of, well, the derivative of y is 1. So it's going to be 0 plus 1, which is 1. Okay. Cool. We have what we need for our recipe. And so what this equals is, it's a double integral. Region R, it's going to be 1 minus 1. Oops. 1 minus 1. Okay. Well, 1 minus 1 is 0. And, well, the answer to this is going to be 0. What does that mean? That means that there's no circulation. All right, but what about flux? Because we're asked to calculate the outward flux through the boundary of that region. We need to find the outward flux of this region here. Okay. Well, for that, we shall use Green's theorem in flux form. Here it is, the Green's theorem in flux form. Beautiful. We are going to grab that. Now we must ask ourselves, guys, what is the partial derivative of f with respect to x? What is that? Well, here's f. What's the partial derivative of f with respect to x? Well, 2 times the derivative of x is 1. So 2 times 1 plus y, which gets treated like a constant, would make the partial derivative of f with respect to x 2. Okay? So then what's the partial derivative of g with respect to y? What is that? partial derivative of g with respect to y? Well, x gets treated as a constant, so it's 0, minus 4 times 1, because the derivative of y is 1, so that's going to be -4. So we can set this up then, keeping that in mind. Two plus -4. Well, the answer to that is -2. So -2 gets factored out of the integral, or the double integral. To calculate region R is going to be, this is going to be the area of the region. Guys, it's quarter annulus, which is actually one word. But you know what? Well, actually, I don't know if it's one word. I don't know what it is, but I know it's quarter annulus. I don't know how to spell, guys. Um, let's see. Well, the radius is 4, okay, and the area is is 16 pi, and well, the quarter area is what? 4 pi, right? Because we're looking at a situation where it's like, um, we got a little circle which is marked at um lowercase r equals 1, and then lowercase r equals 4, 1 and 4, but we're not looking at this, we're looking at this area here in quadrant 1. This is the region that we're interested in. I should be specific. Quarter annulus, this is the, here, this is the outer circle. And the inner circle is where r equals 1, and well, the area is pi. And so the quarter area is going to be pi over 4. So we find the quarter annulus area, which I am now going to write as 2 words. Four pi minus pi over 4 equals 16 pi over 4 minus pi over 4 equals 15 pi over 4. Okay, so what does that mean? That means that -2 times the double integral used to calculate our region, well, that equals -2 times 15 pi over 4 equals what? -15 pi over 2. And this is negative, so that means that it's inward flux. This example says to use a line integral to find the area of region R, and R is x, y, and x squared plus y squared is less than or equal to 16. This is also a form of the Pythagorean theorem. Okay, wait. Okay, there we go. A squared plus B squared equals C squared. Only here it's x squared plus y squared is less than or equal to 16, also known as 4 squared. This is a circle C with radius 4. Now, pi times r squared is going to give us the area of that. Um, that is pi times r squared, 4 squared equals 16 pi. Oh, and this whole thing is what we're looking for, so I just shaded this entire circle here. It's that whole region. Um, so the formula to use here, can be written as follows. That is 1/2 times the closed integral to find c of x times dy minus y times dx. Well, we can set up for c the vector r of t. It's a circle, so sine is y and cosine is x. But the radius is 4 squared is 16. The radius is 4 squared. 4 squared. So we'll put a 4 as a coefficient for the cosine, which is the x coordinate, and a 4 as a coefficient in front of the sine, which is the y coordinate. Okay, and a full revolution around this thing is going to be 2 pi. So, t is going to be in between 0 and 2 pi. Now we calculate the derivative. And, well, the derivative is a vector r prime of t. Well, the derivative of cosine is negative sine. And we'll multiply back that 4, so it'll be negative sine of t. And the derivative of sine is cosine, so we'll have 4 cosine of t. What the heck kind of t is that? Wait a second. Hold on. That's an odd looking t. That looks like a y. I did not mean to put that there. But I will, you know what I will put though? I will put an x and y too. Mark the coordinates up top. So this is our x coordinate. This is our y coordinate. And well, this here, ooh, turquoise. I never use turquoise. Isn't turquoise just so pretty? Not as pretty as blue, but it's pretty. Let's do dx dy. Um, so yeah, so we could set this up. A, the area equals 1/2 times the definite integral of 2 from 0 to 2 pi. This is going to be our x coordinate. So we're going to follow the formula, right? So, hey, we want x. Hey, x is right here. Hey, x is 4 times cosine of t. Okay. dy. dy is right here. Hey, dy is 4 cosine of t. And we did something similar to this earlier, but it wasn't exactly this. It was a little different. Now we need y. Hey, y is right here. Y is 4 sine of t. Um, and we need the x, which is negative 4 sine of t. Negative 4, oops, negative 4 sine of t. Negative 4 sine of t. Okay, and this is all integration with respect to t. Um, right, so we can solve this. That is a equals 1/2 times the definite integral from 0 to 2 pi. The integrand is going to be 16 times cosine squared of t plus, because there's a negative here, 16 sine squared of t. Oh, and then what? We can factor out something. Let's do, I'm not gonna do anything like that. Let me just do it like this. 1/2 times 0 to, for, 1/2 times the, 1/2 times the integral from 0 to 2 pi of 16 for cosine squared of t plus sine squared of t, which is a Pythagorean identity. Thank you, Pythagoras. 1. And this is dt. This equals 1/2 times the definite integral from 0 to 2 pi of 16 dt. And you know what else that is? Well, that is also um 16 gets factored out, put it over 2 because why not? Times the definite integral from 0 to 2 pi for 1 dt, which equals 8 times the definite integral from 0 to 2 pi for 1 dt, which equals 8 times t evaluated from 0 to 2 pi, which equals uh, well, 16 pi. That's our answer. Let's talk about divergence of a vector field. Divergence of the vector field of a vector field in R2 in the second dimension, it's shown here. That is vector f equals f and g, and the divergence of vector f equals the partial derivative of f with respect to x plus the partial derivative of g with respect to y. In R3, in the third dimension, if you have vector f equaling f, g, and h, then the divergence of vector f equals the partial derivative of f with respect to x plus the partial derivative of g with respect to y plus the partial derivative of h with respect to z. Um, we went over this a little bit before, but I think that it's important to reiterate this concept that this upside down triangle, it's called the del operator. And remember, we said it's like a pocket where we hold all of our derivatives. Um, and so this is the gradient, and it's like a vessel that holds all of our derivatives for our x component, our y component, and our z component respectively. And if we take the del operator and we dot it with vector f, then we get the following. That is the partial derivative with respect to x, the partial derivative with respect to y, the partial derivative with respect to z dot f, g, and h respectively, which then you add together, via the dot product, and it becomes the partial derivative of f with respect to x, the partial derivative of g with respect to y, and the partial derivative of h with respect to z. So the definition here, it's shown on the bottom, just to reiterate, but the thing is like if the divergence of vector f equals the equals, if the divergence of f equals 0, then vector f is source free. Means that there is no source. There is no point in the vector field uh, where there are arrows coming out of it, and we'll get into that in a bit more detail in a minute. Yes. So divergence and curl. So divergence in the context of vector calculus measures the net rate at which a vector field expands outward from or contracts inward toward a specific point, acting as a source or a sink. So here there's like a image I drew. This is in R2, the second dimension, but you can expand upon it in R3, just add a height. But essentially, the idea here is that, if you have the arrows coming out, and it doesn't have to be at the origin, but if you have arrows coming out of something, right, that would be a source, right, because it's acting as a source for this force, for the motion here. And if you have a sink, which is here, then you have all of the motion, like the vectors are pointing towards a particular area. Now, a curl a curl measures the microscopic rotation or the swirling intensity of a vector field around a specific point. Um, Divergence of a vector field. The divergence is calculated using the dot product. So here is a refresher on what is going on, how to take the dot product of something. This is in R3, but essentially, if you have two vectors and you want to dot them together, um, the process is where you take a sub 1 and you take b sub 1, and then you multiply them together. You take a sub 2, b sub 2, multiply them together, and then you take a sub 3 and b sub 3 and you multiply them together, and then you add all of those results then you add all of those results together. Um, and well, the del operator, well, you could think of it as a vector made purely of instruction to take the partial derivatives. It does not do anything by itself. It's just waiting for a function to act on. And the operation, when you take the dot product of the del operator and your vector field, you pair them up component by component, as you could see with the a sub ones, a sub twos, a sub threes, b sub ones, b sub twos, b sub threes, and then you just you pair them up, you multiply them, and then you add them. And so um, uh, here, this is what that looks like. But the result is scalar, and the result is scalar because it's a dot product. The vectors vanish. The answer is not a new vector direction. It's a single number or a scalar function telling you the strength of the expression. Telling you the strength of the expansion or contraction at that specific point. Um, so just to reiterate, the dot product and the cross product are different. So if you take the dot product of something, if I take the dot product of vector A dot vector B, that's different than if I take the cross product of vector A cross vector B. In vector calculus, you cannot use these two multiplication symbols synonymously anymore. In the third dimension, it changes. And when you get into three space, the dot and the x mean different things. The dot is the dot product, and um, the x is the cross product, and we will get into that in just a minute here. First, we're going to talk about source-free vector fields. So if the divergence of vector f equals 0, then vector f is source-free. What does that mean? Well, that means that whatever flows into a region must perfectly equal what flows out. There is no magical points that create new fluid or sources, if you want to think about it as like in terms of fluid. It doesn't create any more, like new fluid, and it doesn't drain or swallow any fluid, which would be the sinks. Um, I like electrical engineering, so to draw a parallel between this concept and electrical engineering, this is exactly how magnetic fields behave in the real world. The magnetic field lines, they always form closed loops in theory. There is no isolated north or isolated south magnetic poles. Therefore, the divergence of a magnetic field is always zero, theoretically speaking. Um, the radial vector field shortcut is shown right here. And this is the divergence of radial vector fields. For a real number rho, the divergence of the radial vector field, vector f equaling vector r over its magnitude, the absolute value of vector r raised to the power of rho, equals x, y, and z over x squared plus y squared plus z squared raised to the power of rho over 2, a fractional exponent there. And thus the divergence of vector f equals del dot vector f equaling 3 minus rho over the absolute value of the magnitude of vector r raised to the power of rho. Now this is where we get into the cross product. This is where we get into the cross product, as it does differ from the dot product. And this is what we're dealing with in vector calculus and in R3. Okay, so the curl of a vector field, vector f, is the cross product. In R2, vector f of x and y equals f and g, and the curl is found by taking the partial derivative of g with respect to x and subtracting the partial derivative of f with respect to y from it. Now in R3, vector f of x, y, and z equals f, g, and h, and the curl is found differently. It's found by taking the gradient and crossing it with vector f. So here's the definition. If you have vector f of x, y, and z, and it's differentiable in the third dimension, then this is how you would find the cross. This is how you would find the cross product. Now we have I hat, we have J hat, we have K hat. So I don't think I've ever gone over this on my channel before. Essentially, what you do is, well, you line it up, you line everything up, and you have this is called I hat, this is called J hat, and this is called K hat, and it's always set up in a particular manner, such that you set up this sort of matrixy looking thing, and well, you 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 take something. Let me show the template here. Um, you take something, you subtract it, you subtract from that something, right? And that is going to be your I hat. Then from your I hat, you will always subtract what you get for your J hat. That is, you take something, and then you subtract something else from that, and then that is your J hat. And then when it comes to your K hat, you always add here, and from that, so you will have something, you subtract something from that, and then um, that is your K hat. So hopefully it will make a little bit more sense in that. Um, if I want to find what I'm going to fill these blank spots with, this is always going to be the template setup. It's always going to look like this. Sign changes can vary depending on what you have set up inside of your matrices, but this is how you would find how to fill what's in the blank spaces there. So first we do the I hat. I'll take my I hat and I'll circle it, and I will cross down vertically and I will cross horizontally. And then I'm left with this sort of matrix-like thing where I take the discriminant. So I will take this here and I will multiply it to h, and then I will be left with the partial derivative of h with respect to y. And from that, I subtract what I get when I take the partial derivative of z and multiply it to, excuse me, the partial derivative with respect to z and multiply it to g, and I will get the partial derivative of g with respect to z. So that's what goes into the first part of our operation there. Then I move on to my J hat. And so I will circle it. Um, I will cross out a vertical, and I will cross out horizontal, and I am left with this thing. It's not exactly a matrice, but it's acts at we take the discriminant of it. So pretend that this isn't there because it's crossed out. So what I will do is I will take the partial derivative with respect to x. I will multiply it um, to h, and I will put it into the blank here. That is the partial derivative of h with respect to x. And from that, I will subtract what I get when I multiply the partial derivative with respect to z to f, and I will be left with the partial derivative of f with respect to z, and that will be my j hat. Then as for the k hat business, the k hat business is I'm going to circle my k hat, and I'm going to cross it out vertically, and I'm going to cross it out horizontally. And I'm going to take my partial derivative with respect to x, and I'm going to multiply it to g, and I will be left with the partial derivative of g with respect to x, and from that I will subtract what I get when I multiply the partial derivative with respect to y to f, and I will hit the partial derivative of f with respect to y, and that will be my k hat. And so that is how you will calculate the curl in the third dimension. And here is our textbook definition here. It says the general rotation vector field, vector f equaling vector a cross vector r, where the non-zero constant vector vector a equals a sub 1, a sub 2, a sub 3 is the axis of rotation, and vector r equals x, y, and z. For all non-zero choices of vector a, the absolute value of del cross vector f equals 2 times the magnitude of vector a, and del dot vector f equals 0. If vector f is a velocity field, the constant angular momentum of the field is shown as follows. That is w. I'm pretty sure that's w and not omega, but regardless, it's to show the constant angular momentum of the field. That might be omega, but I'm not sure. Equals vector equals, yes, the magnitude of vector a equaling 1/2 times the magnitude of del cross vector f. One thing to note is that if, going back to the curl here, if the curl of vector f equals the gradient cross vector f, and if that equals 0, then vector f is irrational. So let's talk about curl of a conservative vector field. Just remember that a conservative vector field is a vector field that is a gradient. Now, if we let vector f be a conservative vector field on an open region D in 3 space, we can let psi be a potential function with a continuous second partial derivative with vector f equaling del psi, that is the gradient psi. Then del cross vector f equals del cross del psi equals 0, and if that's the case, then vector f is irrational. If vector f is a conservative vector field, then the following 4 statements are true. There exists a potential function psi such that vector f equals the gradient psi. The second statement is that the integral of the curve vector the vector f dot our velocity vector dr d vector r, that equals psi of b minus psi of a, and well, if we have the closed curve for that same integrand, vector f dot d vector r equals 0 is going to equal 0, and for well, the gradient cross vector f equals 0. Now there's properties of the divergence and curl that we can go over as well. I'm not going to get too into this, but these are some of the mathematical properties of divergence and curl respectively. The product rule for divergence, if we let u be a scalar valued function and vector f a vector field on region D, suppose both u and f are differentiable on D, then the gradient del dot u dot vector f quantity equals del u dot vector f plus u dot del times vector f. The divergence of the curl, suppose that, if you have vector x, y, and z equaling f, g, h, where f, g, and h have continuous partial derivatives, then it's such is true that del dot del cross vector f quantity equals 0, and then the derivative is 0. All right, here's an example, and this prompts us to find the divergence of vector f with its x component equaling x squared minus y squared, its y component equaling y squared minus z squared, and its z component equaling z squared minus x squared. So let us look at our notes here. And well, this shows us how to take the divergence of such a vector. This is going to show us right here how to this is our golden ticket to take the divergence. Now, I'm gonna look at this and I'm gonna say, okay, all right, the divergence of vector f, that's gonna equal the gradient dot vector f. And well, the del operator, our gradient, this is just a little pocket where we hold all of our partial derivatives. And so well, that means that another way that I can write the del operator, the gradient, is as follows. Okay, so I replace the del operator with my partial derivatives and notice that it's being dotted with vector f. And I know what vector f is because it's right here given to us. And so well, that's what the setup is going to look like for that. Now you might say, Stella, that doesn't that looks different from our definitions here. See, because we have the partial derivative of f with respect to x, we have the partial derivative of g with respect to y, we have the partial derivative of h with respect to z, and that looks different than what we have. Well, the reason for that is because, well, you know, another name for the x component here is f. Another name for the y component here is g, and another name for the z component is h. And all of these components, they line up together. This one goes with this one goes with that, and this one goes with this one. So another way that I could write this out is as follows. Well, right. So this is how we would calculate the divergence of f. So what's the partial derivative with respect to x of x squared minus y squared? In other words, what's the partial derivative of f with respect to x? In other words, what's the partial derivative of x squared minus y squared with respect to x? Well, the derivative of x squared is 2x, and since we're taking the partial derivative with respect to x, y gets treated as a constant, so it's going to be minus 0, and well, that's just going to be 2x. So we'll move on to the next term in the equation here, in the operation that is the partial derivative of y squared minus z squared with respect to y. Well, the partial derivative, the derivative of y squared is just going to be 2y. And since it's the partial derivative with respect to y, this z squared gets treated as a constant, so it's going to be 2y minus 0. And well, we can move on to the next one, that is the partial derivative of z squared minus x squared with respect to z. So we're going to add what we get from that. Now, if we take the partial derivative of z squared with respect to z, that's going to be 2z. And since we're taking the derivative with respect to z, x squared gets treated like a constant. Thus, we're going to have 2z minus 0. And, well, as it turns out, this is going to be our answer. The divergence of vector f equals 2x plus 2y plus 2z. Now, let's see what's going on here. We're asked to find the divergence of vector f for vector f equaling x, y, and z over x squared plus y squared plus z squared, all raised to the power of 2. And oh, they were just so kind to us. They gave us this formula here that it equates to be vector r over vector r's magnitude raised to the power of 4. Now, let's see here. This is the formula. This is the formula that we're going to use for that, right? This is the formula here. Um, this is for radial fields, okay? So they just gave us the information telling us that this is a radial field. And well, to that we say thank you, and well, our lives are made a little bit easier. And so, we gaze at this, and from this we can figure the following. That is, the divergence of vector f equals 3 minus rho over the magnitude of vector r raised to the power of rho. Now for radial fields, vector f equals vector r over vector r's magnitude raised to the power of rho. And here, rho equals 4. So then we can just plug this into our formula to calculate the divergence of vector f. Let's see, 3 minus rho, and rho equals 4. So we'll have 3 minus 4 up top. On the bottom, it's a vector r's magnitude raised to the power of rho, which is 4. So raised to the 4th power. Now, well, that equals 3 minus 4, well, that's going to be negative 1. And we'll leave the denominator the same for now. Because, well, when we look at the denominator, vector r's magnitude, the absolute value of vector r raised to the power of 4, it looks like that is given to us right here. So if that's given to us right here, we can put the denominator as x squared plus y squared plus z squared quantity raised to the power of 2, because that was given to us in the prompt, and it's shown that these equate out to be one another, and the numerator is going to be negative 1. And so that is how you would find the answer to a problem like that. Now we're asked to find the curl of vector f, where vector f equals x squared minus z squared in the x component, 1 in the y component, and 2 times x times z in the z component. So we need to find the curl. So to find the curl, we're going to look at our notes here, and we're going to go, oh, and we're going to see this, and so what we're going to do is we're going to set up our 3x3 matrix looking thing with I hat, j hat, and k hat. And so that's how you'd set that up. And we want to calculate the curl. And one thing to note is that curl, well, maybe I should be specific here. Move that over here because I want to show that curl is the del operator cross vector f. We are taking the cross product of the gradient cross vector f, and that's why we have these partials here in this second row here. Now remember, when we look at this, we're gonna use our template here. We're gonna use our template here. This is how I like to set this up when I do the cross product, because it's a lot easier to commit the following to memory: blank minus blank. I might need more room. Blank minus blank I hat minus, because you're always going to subtract what you get when you do j hat, minus blank minus blank j hat, plus, because you're always going to add what you get when you calculate your things for k hat, plus blank minus blank k hat. All right, so that's the template setup. It's a lot easier to commit that to memory than trying to just brute force your way through, or I don't know. This is how I do it, guys. So so let's just try to see what's going on. I'm gonna try to solve this thing. What I'm gonna do is I'm gonna circle my I hat. I'm gonna cross down, and I'm gonna cross off to the side, and I'm gonna turn my attention to this 2 by 2. It's 2 by 2 matrix looking thing, and I'm going to take the determinant. I think that's what it's called, and I'm gonna do the partial derivative with respect to y times 2 times x times z. And, well, I'm going to put the result of that right here in this first section is the partial derivative with respect to y of 2 times x times z. Oh, I'm running out of room. Just squeeze that on in there. There we go. And then from that, I will subtract the partial derivative with respect to z of 1. Okay. Yeah, we're gonna need some more room. That's gonna be the partial derivative with respect to z of 1. All right. And that's gonna do it for our I hat. Then I'm gonna move on to our j hat. I'm gonna circle it, cross off what we have vertically, cross off what we have horizontally, and then I'm gonna be left with this. And then I'll calculate the determinant. I already know I'm gonna need more room. Hold on. The determinant, so what is this? The partial derivative with respect to x of 2x times z, right? Okay, and then what? We're going to subtract from that the partial derivative with respect to z of x squared minus z squared. And that's gonna do it for our j hat. So we're gonna set our sights onto our k hat. So let's do the partial derivative with respect to x times 1. And from that we will subtract the partial derivative with respect to y of x squared minus z squared. Oh yes, we're gonna need more room. All right. That'll be our setup there. So the first thing to do is that we need to take the partial derivative with respect to y of 2 times x times z. So we need to take the partial derivative of 2 times x times z with respect to y. Well, there's no y variable in here, and everything gets treated as a constant. So essentially, we're going to have 0. Then from that, we will subtract what we get when we take the partial derivative of 1 with respect to z. There is no z in there, and 1 gets treated as a constant. Well, 1 is a constant. And so, well, the answer to that is going to be 0. So 0 minus 0 is what we're going to get for our I hat. From that, we will subtract what we get when we take the partial derivative of 2 times x times z with respect to x. Now, 2 and x, excuse me, 2 and z, well, those are constant multiples, and z is getting treated like a constant. The derivative of x is 1, so we're going to have 2 times z times 1, which is going to give us 2z, I think. And then from this, we will subtract what we get when we take the partial derivative of x squared minus z squared with respect to z. And, well, x squared gets treated as a constant, so it goes to 0. So we're going to have 0 minus what we get when we take the derivative of z squared, which is going to be 2z. So 0 minus 2z equals negative 2z. And that will be our j hat. As for our k hat, we're going to take the partial derivative of 1 with respect to x. Well, that's just going to be 0. And from that, we will subtract what we get when we take the partial derivative of x squared minus z squared with respect to y. Well, there's no y in here, so that's also going to be 0. And that'll do our k hat. Now, if we look at this, we have 2z minus negative 2z. Well, that's going to turn into a plus. But the thing is it's like we're subtracting this from 0, so it's going to become a negative again. So 0I hat minus 4z j hat. That's going to be negative 4z j hat plus 0k hat plus 0. Well, that's going to be our answer. Negative 4z j hat, and we can put this into our vector form as well. And so that's what this would look like in vector form. So this is how you would calculate the curl of vector f. You take the cross product of the gradient and vector f. And so this is our answer. Here's a proposition. The proposition is that we want the proposition is that the gradient of 1 over the magnitude of vector r raised to the third power equals negative 3 times vector r over its magnitude raised to the fifth. And we're asked to write a proof for this. I will try. And, well, I will start by trying to transform. Oh, okay. All right. All right. So I will start by trying to transform this here. We have a magnitude vector. We have the vector. We have the magnitude of a vector. We have the magnitude of a vector. And, well, the magnitude, like, let's just turn our attention to the denominator here. Let's see here. The magnitude of this vector. Well, we know, right, that if you're going to take the magnitude of some vector f, to find that, you got to break it up into its components and stick it under a radical. So in the radicand, it's going to be a squared plus b squared plus c squared, or whatever you would like to use for the components. F, G, H, X, Y, Z, alpha, lambda, omega, whatever you'd like. Now in this case, I'm going to use X, Y, and Z because I feel like that might be the move here. So by definition, this is what the calculation of a magnitude looks like. The variables are interchangeable. It's just the concept that we are exploring, the operation, if you will, the operator. So the magnitude, so instead of writing the magnitude of vector r raised to the third power, we're going to write the square root of x squared plus y squared plus z squared. Just another orientation of the same exact thing. Note that it is raised to the power of 3, so we make it parenthetical and raise it to the power of 3. That 1 stays the same. Now there is a root rule, or the laws of square roots, the laws of exponents. If we have the square root of some number with index n x raised to some power m within the radicand, that equals x raised to the power of m over n. Pretty sure that this is the same thing as the square root with index n of x raised to the power of m equals x raised to the power of m over n. I'm pretty sure that's the same exact thing. And I'm pretty sure it's the same thing because, you know, they don't the square root and an exponent, like they are they are inverses of one another. And so if that's the case, right? Um x squared plus y squared plus z squared raised to the fractional exponent 3 over 2. So now we've gotten rid of the square root sign. 1 stays in the numerator. Okay, but then we can bring that upstairs and just make the exponent negative in such a way that we now have. Do I do double parentheses? Yeah, I think I do. X squared plus y. Wait a second, I just realized something. Z needs to have an exponent too. It needs to be squared. Um, X squared plus y squared plus z squared raised to the power of negative 3 halves. We've established, right, that, and I'm just going to write out another definition here. Gradient just means, like, partial derivative with respect to x, partial derivatives with respect, partial derivative with respect to y, partial derivative with respect to z, right? So if we let m of x, y, and z equal x squared plus y squared plus z squared, and we remove the gradient, oh well, z squared raised to the power of negative 3 halves, and we remove the gradient, that means that we are now bound to take the partial derivatives of this expression x squared plus y squared plus z squared raised to the power of negative 3 halves with respect to x, with respect to y, and with respect to z. Because that's what the del operator does. What's being asked? Take the partial derivative of this. What even is this? I don't even know. This is a chain rule situation. Chain rule. Dude, there's construction going on and sirens blaring outside. Okay, that's the chain rule. So that means I have to set an outside function and an inside function. So if I think that I'm going to set the inside function as g of x equal to, I think I'll set that equal to x squared plus y squared plus z squared. So then, so then, so then the derivative of this function with respect, the partial derivative even, like the partial derivative of this is with respect to uh with respect to x is going to equal what? 2x. And what's more is that if I put like a u substitution, if I said that like, okay, then we're gonna do the power rule here. Set u, okay, no, okay, yeah, f of x equals u placeholder variable raised to the power of negative 3 halves, then then f prime of x, equals negative 3 halves u raised to the power of 3 halves, negative 3 halves minus 1, so what is this, negative 5 halves? Something like that. So then now we apply the chain rule. Now we apply the chain. You know what? You know what? I'm gonna use my shrink ray. Um, and I'm gonna use my shrink ray. Oh, okay. So now I use these components to put the chain rule back together. So that's gonna be f prime. So that's gonna be negative 3 halves times the inside function x squared plus y squared plus z squared times the derivative, right? I don't even have to do times, just do. No, I will. You do have to do times. I was just not gonna put the dot there. No, you know what? I'm not gonna do the dot because like the dot means like different things in different contexts in this section. So I'm just gonna say 2x because we're not. Yeah, I mean, not that you could take the dot product of those, but you know, maybe you could. I don't know. If math goes on forever, then technically speaking, there probably is a way that you could dot those together, even though they're not vectors exactly. But I'm pretty sure that's the answer for the partial derivative of x squared plus y squared plus z squared raised to the power of negative 3 halves. Just kidding, no, it's not. Oh gosh, right? Because we applied the power rule to this inside part. So negative 5 halves. All right. So the partial derivative with respect to x for x squared plus y squared plus z squared raised to the power of negative 3 halves equals negative 3 halves times x squared plus y squared plus z squared quantity raised to the power of negative 5 halves um, times 2x. All right. And now, just looking at the nature of this, I don't even think I have to like retake all of the derivatives again. I think that I could just all I have to do is just switch out this 2x with the corresponding variable, right? So I'll be thorough here, at least for this part. Instead of redoing the chain rule, we could just use our pattern recognition skills to be like, hey, everything's going to be the same except for the variable on the tail end of this. I'm pretty sure. Everything else is going to be the same. It's still going to be raised to the power of negative 5 halves because the procedure to find these things are the exact same. So then in this case, this was with respect to x, so now this is going to be with respect to y, thus in the tail end it's going to be 2y. This is supposed to have, this is supposed to be squared, I just realized. But we're going to move on to this one here. And then this at the tail end is going to have 2z. That's the only thing that really changes, I think. So, so what's going on? Well, the partial derivative of x squared plus y squared plus z squared raised to the power of negative 3 halves with respect to y is going to equal negative 3 halves times x squared plus y squared plus z squared raised to the power of negative 5 halves times 2y, and then the partial derivative of x squared plus y squared plus z squared raised to the power of negative 3 halves with respect to z is going to equal negative 3 halves times x squared plus y squared plus z squared raised to the power of negative 5 halves times 2z. This entails like the gradient of m, right? This is del m equals what? The del operator, del 1 over the magnitude of vector r raised to the power of 3. And we make the assertion that we can set that these are equal to one another. Let's spread that out. Why not? Now we can put this into vector form. What do we have vector r is set to again? I think my one brain cell made a connection with itself. It folded back over into itself. Because I think that uh so 2x, right? 2x, or just even 2 times 3 is 6. Divided by 2 again is 3, so negative 3 in the numerator. And then take that x with it, because that x isn't going to be able to cancel with itself. Um, okay, take this here, and we stick this back into the denominator so we can make this a positive 5, so we can make this expression raised to the positive exponent 5 halves. But then we could put it into root form. So here's what I'm trying to say. We could put it into root form. So what I'm saying is that, you know, uh, now we have negative 3x times 1 over um, the square root with index 2. Okay, so here's what I'm saying. I'm like, do I even know what I'm saying? Okay, wait. So here's what I'm saying, right? So this is going to be like x squared plus y squared plus z squared raised to the positive 5 half power over 1, and I'm saying that, well, this is the same thing, right? I'm putting it, remember when we took this rule, we started undoing it, we're putting it back together. This is negative 3x on the numerator, and then I'm putting it back into root form. This is index 2. This is going to be x squared plus y squared plus z squared, but this time, instead of being raised to the power of 3, um, now it has to be raised to the power of 5. Okay. So, by definition, this Index 2, this square root of x squared plus y squared plus z squared, by definition, is the magnitude of vector f, but for us it's vector r, right? So, right, so, uh, for us it's vector r, but instead of being raised to the third power, it's now raised to the fifth power, right? So this is the same thing. I'm saying that this inside of the parentheses here is the same thing as vector r, so I can say that this is going to be the absolute value, or rather the magnitude of vector r raised to the fifth power. Okay, so then that's going to do it for our x component. As for the y component, it's very similar, except for instead of negative 3x, it's negative 3y. Still the same thing with the denominator. Nothing changes in the denominator. Um, okay, and then for z, it's the same thing. It follows suit. That is the magnitude of vector r raised to the power of 5. But now it's like, okay, this the proposition is that this thing, the gradient of 1 over the magnitude of vector r raised to the third power equals negative 3 times vector r over the magnitude of vector r raised to the fifth power. That this doesn't look like that yet, because you know it in since this is a vector, we can actually factor this x, y, and z out because everything else is the same. So I can factor out this x, y, and z. I can factor that out, and then I could have this multiplied to uh let's see, I don't think I need that much room. I could have this multiplied to negative 3. What happened? There we go. I could have this multiplied to negative 3 over vector, the magnitude of vector r raised to the fifth. And that is the same thing as negative 3 times vector x, y, and z over the magnitude of vector r raised to the fifth. But the thing is, so if we look at this formula here, the absolute value or the magnitude of vector f equals the square root of x squared plus y, excuse me. So if we look at this formula here, the absolute value of vector f, the magnitude of vector f equals the square root of a squared plus b squared plus c squared. Okay, so that means that vector f, okay, right, but we didn't specify that, but we didn't specify that, right, that like vector f by itself, it's a vector f, so that is including, point A, B, C vector, which is really, x, y, and z. But just because we're doing this in a formula form, this is probably, I mean, you could do it this way. X, Y, and Z are just placeholders. They just mean something. They're interchangeable variables, standardized that you do X, Y, and Z, but this is, honestly, here. I feel like I'm making this more confusing than it has to be. You know what? You know what? Here. That's X, Y, Z. This is X, Y, Z. And you know what? While we're at it, we don't even have to call this vector f. Let's just call it vector r. Let's just call it vector r. Why not? Yeah, I feel like that makes more sense. That's more mathematically sound, isn't it? What I'm trying to say is that vector r equals vector x, y, and z, right? And so um, since that's true, then this thing on the numerator, this can be changed such that this equals -3 times vector r over the magnitude of vector r raised to the fifth power. And that was the proposition to begin with. And so this is the proof that this proposition here is correct. And we've just shown that mathematically. Surface integral of a vector field, guys. This is how you do that.